Welcome to the Digital System Design Laboratory. So today in this video, we are going to perform our experiment number 4. And the objective of this particular experiment is to implement the Boolean expression in SOP and POS form, where this SOP stands for sum of products and POS stands for product of sum. So generally, to implement any Boolean expression in these two forms, either a Boolean expression may be given, okay, or there may be a truth table given, okay. So in both the cases, we actually obtain the Boolean expression in SOP form or POS form. Sometimes it may be possible that there may be a statement given, and from the statement we have to obtain the truth table, and from the truth table we have to obtain the Boolean expressions in SOP and POS form. So let us suppose that in this example I have taken that the Boolean expression is given like f equals to a bar c plus b bar c, and this expression we want to implement both in SOP form and POS form. So before proceeding to how to do this implementation, I would like to first introduce a little bit about what is mean terms and max terms. So let's start with this discussion. So let us suppose that we have a truth table which is having three Boolean variables, namely x, y, and z. So as we know that if we have these three variables x, y, z, then each variable can take binary bit equals to 0 or 1. So whenever this Boolean expression is taking 0, I can reflect this x as a x prime, and whenever it is taking x equals to 1, I will be keeping it as unprimed form, means x. So if these three variables will take this 0 and 1, then out of these three variables we can form this total 8 combinations. So once we are able to form this all 8 combinations, then we can define what will be the mean terms and what will be the max terms. So here we can see that in this case, to get the mean terms, we need to perform the AND operation between all the Boolean variables. In this example, we can see that in the first combination, when our x, y, z is equals to 0, 0, 0, in this case, this x will be designated as x prime, y will be designated as y prime, and z will be designated as z prime. So therefore, if we perform the AND operation between all these Boolean functions or Boolean variables, you can say, then we are going to get a term which will be x prime, y prime, and z prime. Similarly, in the second combination here, we can get this x prime, y prime, and z, because z is equals to 1. And therefore, we can have total 8 mean terms that you can see in this particular column. Similarly, we can also get the max terms. To obtain the max terms, what we have to perform is we have to first complement the each Boolean functions, Boolean variables, and then we have to perform the OR operation. For example, here this variable x is taking value equals to 0. So that will be corresponding to x prime. So this has to be complemented. So we will be getting x. Okay. Similarly, here we are getting y prime. So it has to be complemented. Again, it will be becoming y. And similarly, this will become z. So we have to perform the OR operation between all these Boolean variables. So we are going to get this max terms equals to x plus y plus z. And similarly, you can opt in all other Boolean means max terms by following these combinations and just taking the complementing each of the variables and then performing the OR operation between all the variables. Here you can see that this mean terms and max terms, if you take the complement of this particular mean term, like x complement, y complement, z complement, if you take the whole complement, this will become your x plus y plus z. And therefore, what we can say is this mean terms and max terms are complements to each other. Okay, that you have to remember that this mean terms and max terms are generally complement to each other. Okay, and here this mean terms is also referred as like standard product term. Okay, it is also called as the standard product. Either you can say it is main terms or you can also say it as the standard product. So why it is standard product? Because this AND operation is actually being performed for all the variables, all the Boolean variables. So here it is having just 3 variables. So all the 3 variables are actually present in this particular product, because AND operation is actually denoted by dot, okay, and therefore it is also referred as the standard product. You remember that each variables in any Boolean function, for example, here we have this Boolean function, so each variable, whether it is a primed form or unprimed form, it is known as the literals. So I have written over here that this mean terms are also called as a standard product because it contains all the literals. So the meaning is that it is containing all the Boolean variables. Similarly, max terms are also called as standard sum. Okay, it is a standard sum because it is also containing all the Boolean variables, whether it is in the primed form or unprimed form. So once you understood this mean terms and max terms, then we can go on seeing that what are the different forms in which this Boolean expressions can be represented. For example, here we have already one function f which is equals to a bar c plus b bar c. So basically this representation is also known as the minimal SOP representation. Okay, this is also called as the minimal SOP, means minimal sum of product form. So this function itself is given in the form of minimal SOP, okay, which is the standard form representation of a Boolean function. So let us suppose that if this particular standard form or minimal SOP form is given, okay, then from this given function itself, as I said, that whenever we have any variable x, y, z or a, b, c, d, whatever, it is going to take either value equals to a Boolean means bit 0 or bit 1. So whenever it is bit 1, the variable will be referred as x. Okay, whenever it is 0, it will be referred as x bar or x prime. Okay. Similarly, if we have this function f, okay, then from this function f, okay, we can form a truth table. And how it can be formed? To form the truth table, we have to take all these 3 variables first, and then we have to write all the possible combinations in the truth table. And then we have to mark those places. If you substitute the values of a, b, c in this particular expressions, you are either going to get 0 or 1. Okay. So if you substitute all the values, you will find that for the first combination, when it is 0, 0, 0, you will find that this function returns you value equals to 0. Similarly, if you write this second combination, here you can see that c equals to 1 and this a and b is equals to 0, 0. So if you substitute here, you are going to get this value equals to 1 multiplied with 1 plus 1 multiplied with 1. So ultimately you are going to get this result equals to 1. So you remember that this we are actually seeing multiplication, but generally it is a dot. Okay, when we refer this like a dot c or a bar dot c, but this dot or multiplication, we mean to say that it is an AND operation, that you remember. Okay. Similarly, this plus signifies your OR operation. Okay, it is not a general sum that we do in our mathematics, but rather it is a logical operation or operation. Okay, so this way we are going to we can construct our truth table. Okay, based on this combination, and then if you substitute this combination of your ABC, then we are going to get sometimes this function will become 0 and sometimes it becomes 1. So this way we are going to construct our truth table. Now, if you see, this was already given in the minimal SOP form. Okay, so now what we can have is we can form a canonical form representation. Okay, you remember that it is a minimal SOP form, but we can have another form in which this all the mean terms will be available. For example, here you can see that whenever this function is taking the value equals to 1. Okay, let us say it is having a certain outputs for a certain combination of inputs, it is going to be high. Okay, so if we take all these values equals to high, and if you combine all these mean terms, okay, then you can have this a function f. Okay, so here you can see that this combination is giving you this mean terms for this particular output. 1 is nothing but your a dash b dash c, okay, or a bar b bar c. Similarly, for corresponding to this one, we are going to get this output equals to a bar b c. So here we are going to get a bar b c, and similarly for this, we are getting this a b bar and c. So this way we are going to construct our function f, okay, and this function is going to give you values corresponding to the combination of a, b, c, and then this is going to return you value equals to 1 for these mean terms only. Okay, for these mean terms, this function is going to give you value equals to 1. Now you can compare this particular function f with this particular function f. In this particular function, you can see that it is not containing means a standard product term. It is containing just a minimized product term, okay, in which we have already reduced one of the mean terms also, and we have already reduced one of the literals also. So in this case, you can see that it is a minimized expression, okay, and here it is having the its canonical form, in which we are having the all the possible mean terms, okay, which is nothing but our standard product term, which is containing all the literals, okay, it is containing all the literals. So in this particular experiment, we are actually going to conduct an experiment or to implement a circuit that will be available in the SOP form. You remember that it is actually, we generally write like SOP or POS implement, but here we are going to implement a SOP implementation. That means the sum of standard product. You remember that it is sum of standard product. It is not just like a sum of product, but whether it is actually your sum of the standard products, or it is a sum of mean terms. Okay, so you remember that it is a sum of mean terms. So if you reduce this function, obviously you are able to get this function. Okay, so this way you are going to get this particular function, but we are going to actually obtain our or perform our experiment, or we are going to implement the circuit in SOP form, okay, which is a canonical representation. So here you can either you can also means implement the circuit by following this minimal SOP form. Okay, in this case the circuitry will be very simple. Okay, and we can also go for this implementation. So here in this experiment, I'm going to implement this one, okay, which is also known as the disjunctive canonical form. You can find out in the books that it is written as the disjunctive canonical form. Okay, so now here you can see this implementation is very fairly simple, because we have to perform the OR operation. First, we have to perform the AND operation between all the variables. Maybe it may be available in the primed or unprimed form, or then we have to perform the OR operation. So here you can see that we are having this AND gate to perform all the AND operations, and then we are having this OR gate, and then finally we can implement this function f. Now, one more thing, suppose as we have taken this mean terms corresponding to 1, okay, we are just performing the ORing operation of the mean terms corresponding to f, where it is f equals to 1, then we are going to get this function f. What if we take this zeros? Okay, if we add all the zeros, okay, all the mean terms corresponding to f equals to 0, then that is going to give you f complement. You remember that you can verify that this will be going to give you f complement. F complement will be available if you take this zeros only. Okay, so once you will getting this f complement, okay, you can write all the mean terms corresponding to f complement. That will be your a bar, b bar, c bar. Similarly, it is here a bar, b, and c bar. Okay, a bar, b, and c bar, and here it is a, b bar, c bar, and so on. So you are going to get this 5 means mean terms, and addition of this or the ORing operation between them. So that is going to your f bar. Okay, so now to get this function f, okay, what we have to perform is we have to just take the complement of this. So once you will complement this, you are again going to realize the function f. Okay, so if you do that, you are going to if you take this complement of this particular entire function by following the De Morgan's theorem, obviously the function that you are going to get is a plus b plus c in bracket, then again dot, then you are going to get a plus b bar plus c, and so on. So that will be your POS implementation, means product of sum, or in a more specific way, you can set it the canonical form, and it will be your POSS form. Okay, means product of a standard sum. Okay, it will be a standard sum. So that way we can also implement our circuit. So here you can see this. If you take this zeros, okay, into the consideration, you are going to get this type of functions. Either you can take the direct functions, okay, directly you can say by just taking the all max terms into the consideration, or you can just calculate the way I have shown in the previous case. You take the f bar and then you can calculate the complement of this. So it is going to give you this particular form POSS, means it is product of a standard sum. And this way we are going to have our function f. Okay, so this function can also be implemented here. You can just understand that in the previous case, what we did is we first perform the AND operation and followed by the OR operation. Here we have to first perform the OR operation and then followed by the AND operation. And you can understand that these two representations should be equivalent, and it is going to implement the same function. So here you can see that we have two different functions for f. Okay, for this particular minimized expression, okay, we are going to get this two canonical form representation. One is in the POS format, okay, product of sum format, product of a standard sum format, and another one is product of like sum of standard product format, okay, sum of standard product. So this both the expressions are equivalent, that we can verify by just implementing this circuit. Okay, so here you can remember one thing, which is you can see that this expression is minimal SOP form or simply SOP form. Okay, this can be directly be implemented, or you can also just you take one like here you can take out this C common, and here you can write this function f equals to a bar plus b bar c, and that is called as the minimal POS form or simply POS form. Okay, so it is a product of some forms, so in which we have means eliminated the redundant Boolean variables. Okay, those are not required. So now in this experiment we are going to implement this canonical form, and then we will be verifying that this both the means functions are equivalent. Okay, so let's start this implementation on the MultiSim, and this is another way of representing the same thing. Like this function f can also be represented by this sign, that a sign is represented that it is the product of this max terms, and this max terms is corresponding to 0, 2, 4, 5, 4, 6, 7. So this 0 represents this equivalent decimal numbers. Okay, so corresponding to this 0, this is 0, and then for this particular output equals to 0, here you can see that this corresponding decimal value is equals to 2. Okay, similarly here it is 4, and here it is like 6, and here it is 7. So this way we can write this as the way product of this max terms. Similarly, this can also be represented by the sum of this main terms. Okay, 1, 3, and 5. So this way we can have our canonical representation. So let's start with the implementation part. Okay, in the MultiSim. So I'm just going to the our implementation part. Okay, so here this this is our MultiSim software. Okay, where we have to implement this particular the SOP and POS representation. So you can just go back to this particular circuit. So you can see that here we have to take the 3 input AND gate, and then we have to take the 3 input OR gate. So normally you won't find any 3 input AND gate and OR gate ICs. So I will be implementing the same thing using the available IC, which is a 2 input AND gate and 2 input OR gate. So here you can see that we have 3 variables A, B, C, and we also have to get the complemented form of our B and complemented form of our A. Okay, from this expression itself, we can see that we have this complemented form of B and complemented form of A is available. Okay, and the C is only will be available in the unprimed form, so that we can opt in from a circuit itself. So here you can see that we have to just get the complement. I have just taken this particular IC. This is our 74LS04, which is nothing but our hex inverter. Okay, so from this inverter I can do the complementation part, and I will be just calling this first. This is our supply. Okay, so this will be used for our means giving a variable A, and this will be our B, this will be our C. Okay, so this way I'm just assuming these are our input variables. Okay, digital means Boolean variables. Okay, A, B, C. So now, as I said, that we have to complement the A and B, and we have to take the C as it is. So I'm just doing this first part. Okay, complementation part. Okay, so you just make this connection this way. I'm just first making this connection. Okay, so this is our A. So I will be just connecting it over here. So now this is going to give you, this output is going to give you A bar. Similarly, if you take this one, I'm just again just pull this wire up to this point. Okay, so that I will be able to make a connection easier. Okay, because it is going to be a very complex circuit. So again, you can just connect to this particular thing. Okay, so now this is going to give you your C bar. Okay, B bar, sorry. And here we have this C bar. Okay, so that you can make a connection or like this. Okay, you just pull this wire at this point and then you can make the connections. So after having this, you can see that I have this AND gate here. Again, I have another AND gate, and there here I have the OR gate. So you can think of, because we need the 3-input AND gate. Okay, we need 3-input AND gate because the 3-input AND gate is not available. I am just using the 2-input AND gate, and by using the same 2-input AND gate, I am going to implement the functions. So first you can see here, you can see what are the inputs. It is A is given, then it is B bar is given, and C is as the inputs. So first I am implementing this A B bar, and then the output of this AND gate will be applied to another AND gate, and then the input will be another input will be C. Okay, and that way we can do the implementation. So here you can see that we have to first apply A and then B bar. Okay, so this is our first AND gate. So I'm just connecting this. Okay, I'm just connecting this one. Okay, this is our A, and then we have to connect the B bar. So you can see that this is our B bar. Okay, you can see this one is our B bar. So I'm just connecting this to this particular point. So this is our B bar. Okay, so this way I have made the connection, and this is our output, and that output will be equals to A B bar. And now this has to be applied to our next AND gate. Okay, so I'm just making this connection. Okay, I'm just connecting this, and then again another input to this second gate will be our input C. So you just make this connection like this. Okay, so here I have made this connection. So now this is the output of our this particular gate. Here you can see that this is the output. Okay, this will be our output that will be corresponding to A B bar C, and that has to be applied to the input of our OR gate. Now the second this particular output, this second AND gate, you can see the inputs to this particular AND gate is nothing but your A bar, then it is B and C. Okay, so that we can make a connection like A bar. So let us suppose that this is our third AND gate. Okay, so to this particular third AND gate we have to connect the A bar. Okay, so this is our A bar. Here you can see that this is our A bar. So this should be connected to this. So you can make this connection. Okay, so just I'm making this connection like this. So it has been now connected. Now the other input to this terminal is our B. So you just try to make the connection for B. So this is our B. Okay, so you just take this as a connection. Just make this connection this way. Okay, so now we have connected this A bar and B. Now this will be the output. Okay, of our this fourth gate. Sorry, for first we have to connect from the third gate. Okay, this is the output of our third gate that should be connected to the input of our fourth AND gate. So this is our input to the fourth AND gate. Okay, and this input is same as your like A bar B. Okay, now we have to connect the another input equals to C. You can see here it is A bar and it is B. We have already obtained. Now we have to connect this C. Okay, so we have to connect the C to this particular input. So here you can make this connection directly to this particular C. Okay, now I'm just making this connection. Okay, it is becoming C. Now this output. Okay, this output is nothing but your output of your second AND gate. This output. Okay, this is corresponding to your A bar B C. Now similarly you can obtain this one. Okay, I'm just doing this. It is A bar B bar and C. So you can make this connection. Okay, A bar B bar C. So here you can see that this is our first AND gate. Okay, so here we have to make a connection with the A bar. Okay, so that should be connected to this point. Okay, you remember that this is our A bar. Okay, this is just to make this connection properly. This is A bar, and then again you have to make the connection for example, here it is. You can see that this connection is A bar and B bar. Okay, so this is our A bar. I have just connected. Okay, so we have to make this connection A bar and B bar and then C. Okay. So B bar we have to make a connection. So here you can see that where it is B bar. So just go back again and just try to connect the B bar. Okay, so this is our input. So this should be connected to your this particular output. Okay, this is our B bar. Now this output has to be connected to the another AND gate, and then this should be connected to our C. Okay, here you can see that it is connected to C. Okay, it is C. So now it should be connected to C. So if you go back, so you just make this connection, it has to be connected to C. So this is our C. Okay, so this way we can make this connection. Now this is the outputs. So now you can see that these three outputs of the AND gate has to be connected to the OR gate, and then we have to finally confirm our output. Okay, we have to verify our output. So here you can see this is our first output, okay, of this particular gate that has to be connected to this OR gate. I'm just connecting this to the OR gate. Then this is our second output, okay, that has to be connected to this OR gate. Now this OR gate output, because again it is a 2-input OR gate, so this has to be connected to the next OR gate. Okay, I'm just taking another OR gate. So here it is connected, and then I have to connect this output to that particular OR gate. Okay, to just make this connection at this point. So now this output has to be connected to the LED. Okay, and now we can go on verifying our particular circuit. So let's see. First, this is our A, this is B, this is a C. So first you just make all the combination equals to 0, 0. Okay. So first we have to make all this combination equals to 0, 0, and then we have to verify all this outputs. Okay. So if the circuits are connected properly, okay, all the connections if I have made properly, then only the circuit will work. Otherwise, it will show some error. Okay. So let's start. And before that, as I said number of times, that you please don't forget to give the supplies to each and every ICs. Okay, whatever the ICs we are using, you have to connect power supplies to each and every ICs. Okay, so here I have already connected the 5-volt power supply to each and every ICs, and also I have connected the ground. Okay, I have already connected the grounds. Okay, so you don't forget to do it. Okay, now we have to verify this first combination 0, 0 should give this output equals to 0, 0, because LED should not glow. Okay, LED should not glow. So if you do that, you can see that this LED is not glowing. Okay, this LED is not glowing. So we have tested our first combination. You can stop it. Then you can make this C equals to high. Okay, once you will make this C equals to high, then we are supposed to get this output equals to high. Okay, as per our truth table, this is supposed to be getting high. So we are getting this value equals to high. Similarly, you can stop it, and then again you can test on the second combination 0, 1, 0. That should be equals to 0. Okay, so I'm just making it 0 again. So you can make this equals to 0, and then you can make this B equals to 5 volt. Okay, so if you make this 5 volt, then the output should go 0. So you can just execute it. So here we are able to verify our third combination. Okay, so now you can stop it. We can go on verifying our fourth combination. That will be our 0, 1, 1. Okay, so just make it 5 volt. So once we'll make it 5 volt, then you can see that here in this truth table, when it is 0, 1, 1, the output should be 1. Okay, so this output should go high if we execute it. So let's see. So this LED is now glowing. So it is output is high. So in this way, we have tested our fourth truth table. Okay, fourth combination. Now you can again test our next combination. That will be 1, 0, 0. So you just make it 0 volt. Okay, just make it 0 volt. Then you can again make this also 0 volt. So remember that we are treating this as a C. Okay, ABC. So this first one is our corresponding to A, the second one is corresponding to B, and third one is corresponding to C. Now this has become ABC is becoming 1, 0, 0. So when it is 1, 0, 0, here you can see that this truth table for 1, 0, 0 combination, it should be 0. So let's say if you execute it, you will get this value equals to 0. So now we have already verified our fifth combination also. Okay, so now if you test this one 1, 0, 1, this output should go high. Okay, 1, 0, 1, this output should go high. So that we can test 1, 0, 1. So it is 1, 0, 1. So we have to make this equals to 1. So just I'm making it 5 volt. So if you do this, you will be able to get the output equals to high. So now we are getting this output equals to high. Okay. Similarly, you can stop it, and then you can test the other combinations like 1, 1, 0 and 1, 1, 1. So if you do it, this is 0. This has to be made 5 volt. So just make it 5 volt. If you execute it, hopefully there should be output should be equals to 0. So here it is, we are getting 0. And now you can stop it, and you can finally test your final combination. That will be 1, 1, 1. So now if you see it, if you execute it, we can verify yes. So now we have already verified all this possible combinations in our this SOP form. Okay, this is nothing but our SOP form. Remember that it is the sum of standard product form. So this way we have first implemented our AND gate operation, and then this has to be connected to our OR gate, and then we have to verify our result. So finally, we have to obtain the output of the function, and then we have to verify our truth table, okay, from the given Boolean function or from the given truth table. Okay, we have to verify it. Now, again, as I said, that the same truth table we can again verify if you implement it by having the POS implementation form. Okay, so here you can see that we have this particular case, okay, US form. So in this POS form, first we have to do this all OR operation, and then followed by the AND operation, and then we have to implement this particular function F. Okay, so if you do this implementation, then again we have to verify the same truth table, and it has to be same, because this two representation, as we said, that it is a equivalent representation. Okay, these two are equivalently same. Okay, they are equal. So we have to implement this, and then we have to verify the same truth table. So I have done that. So you can see this is our POS implementation. Okay, so here, just for the simplification, what I did is here you can see that I have just taken this particular key. Okay, it is an interactive constant. Okay, so if you press this A, this will be changing from 0 to 1, or if you press B, it will be changing from 0 to 1. This way you can alternatively change this value from 0 to 1 or 1 to 0. So this particular interactive constant you can get from this. Okay, it is available here. You can go to the sources. Okay, so if you go to the sources, you will be able to find that digital source, and within this digital source you are having this interactive digital constant. Okay, so within this interactive digital constant, you can do this changes. Okay, for example, I have changed this key as A, key equals to B. Here you can also make this key equals to C. So just go to this particular constant and then press the right click button, go to the properties. Okay, and here you can change this key for toggle, and here I can make it C. Okay, so now you can see that these are the three inputs, A, B, and C. Okay, and just pressing these buttons, I can make all the combinations to change. Just to avoid the complexity of the circuit, what I have done here in this case is I have not used the 7404 IC for getting the inverted inputs. Okay, rather I am just choosing the discrete components which is available in the MultiSim. Okay, 7404. Okay, so here you can go to this TTL. Okay, so once you will go to this TTL, here you can get this 74 standards. Okay, here you can get the individual inverter components, or any individual ICs you can also, any individual gates you can also get. For example, if you want to 7400, here you may get these individual or discrete NAND gate component. Okay, rather than the IC. So just to avoid this complexity, but you remember when you performing your experiment in the laboratory, you will be just having the ICs only. Okay, and that time you have to make a connection, as I did in this previous case. I had taken the 74LS04 IC. You have to choose the 74LS04 IC, and then again you have to make the connection in this way to obtain your like A bar and B bar and C bar. Okay, but here, just for the complexity, to remove this complexity, I have used these things. Okay, so this way we can also perform our experiment in our MultiSim. Okay, so here you can see that I have taken 3 OR gates. Okay, you can see I have taken 3 OR gates because the circuit is going to be complex, and finally I'm having on this AND gate. Okay, so I have already connected all the power supply to this all ICs, and then I have connected the required ground. Now you can see this circuit. Okay, here you can see, because it is having 3 input OR gate, because in the IC's form we are just having the 2 input OR gates. So obviously to realize one output, okay, we have to use 2 OR gates. Okay, in the IC. Similarly, altogether, because there are total 5 such 3 input OR gates, so I have to use total 10 OR gates. Okay, 5 cross 2, because for each implementation I require 2 OR gates. So that's why I need total 10 OR gates when we are having just 2 input OR gate. Okay, so that's why I have chosen 3 ICs, because in each IC we are having just 4 AND gate, because I need 10 AND gate, 4 OR gates. We actually require total 10 OR gates, and therefore I have chosen 3 ICs. Okay, so now you try to do this implementation. Okay, so the first part you can see here, the first input should be A bar plus B bar plus C bar. Okay, so just you go back again, and what we have to do is, from the first input I have to connect the A bar and B bar and C bar. So what I am doing is I'm just extending this line over here. Okay, I'm just making this extensions because I have to make the connections. So you can make this extension like this. Okay. In the MultiSim, you will be able to do this. Okay. Even in the breadboard, you have this extensions. If you remember that, how to make a connection on the breadboard, because there are horizontal sorts and vertical sorts. A similar thing you can also perform in your breadboard also. Okay. So now you have to connect this A bar. Okay. So this is our first OR gate. So I am just connecting this A bar over here. Then I'm connecting the B bar. Okay. So this is our B bar now. So now this output has to be connected to your next OR gate, and the another input to this particular OR gate should be our C bar. So I'm just making this connection, and this output now, this output is realized now, and this output has to be connected to our AND gate. That you remember. You can see it, our circuit, this is the output. Okay. This output has to go to our AND gate input. Similarly, the second, you can see it is A plus B bar plus C bar. Okay. A plus B bar plus C bar, that we have to implement. A plus B bar plus C bar. So here I have this our third gate. Okay. So here I have to connect our A and then B bar plus C bar. Here you can see it is A and B bar plus C bar. Okay. So now just connect this A. So I am just connecting this A. Okay. A is available at this point. Okay. So here it is A, then we have to connect the B bar. Okay. So this is our input, another input of this OR gate. So we have to connect with the B bar. So you see this line is B bar. Okay. So now I have connected it with the B bar. Now this output, okay, this output has to be connected to the input of our fourth OR gate. And the another input of this OR gate should be our C bar. Okay, just to make this connection with the C bar. So this is our C bar. Here you can see that this is C bar. Okay, so please don't confuse. This line is corresponding to A bar. This is corresponding to A, and this is corresponding to A bar because it is passed through an inverter. Similarly, here this output is B, and this output is our B bar. Similarly, this is our C, and this output is C bar. Okay, so this way I have made this connection. So now after making this connection, you can see that we have implemented the second OR gate, okay, output. So this output is now available. Okay, this output is now available. Now we have to implement this third OR gate, okay, which is nothing but your A plus B bar plus C. Okay, A plus B bar plus C. So that you remember A plus B bar plus C. So that has to be connected to here. So first we have to make a connection with A. I'm just making with this connection with A. Now we have to connect the B bar. So I'm making this connection with the B bar, and then this output has to be connected to the input of the second OR gate. So it is connected here, and then again a C has to be connected. Here you can see this, it is A plus B bar plus C. So then we have to make the connection with the C. So please you just connect it with the C. So here it is C. So here I have made this connection C. Now this third output is available. Okay, this OR gate, this third OR gate we have implemented, and this output is now available. Now we have to implement this one and this one. So this is our A plus B plus C bar. Okay. So A plus B bar, A plus B plus C bar. So now you can see this is our input. So we have to connect A. So this is to be connected with the A. Then we have to connect the another input with the B. So it is connected with the B. Okay. And then you're again the third input should be our C bar. Okay. So now this output has to be connected to the input of this next OR gate, and then this has to be connected with the C bar. Okay, so I'm just making this connection with the C bar. So here you can see that there are lots of wires, okay, which are connected. If you don't do connections properly, obviously you are not going to get the output. So this is our fourth OR gate output, okay, that we are going to get. Okay, this is our fourth gate output that has to be connected to the this AND gate. Okay, fine. So now we have to make this final connection, which is A plus B plus C. Okay. So that A plus B plus C, I'm just going to connect with this gate. Okay. So this is our A. So here you can just make this connection. This is A. And then this has to be connected with the B. So this is our B. And then this has to be connected to our next OR gate. And then the another input should be your C. Okay. This should be connected to your C. Okay, now you have to make the connection with the AND gate. Okay, all this output has to be connected to the AND gate. So you can see this is our first output of our OR gate, first output that has to be connected with the AND gate. So here it is AND gate, our 74LS08. So another input should be this output, okay, because it is just a 2-input AND gate. This we have implemented this function. Okay, you see this This 2 has to be connected. This we have already connected with the AND gate, and then we are going to get the output, and that output again has to be applied to another AND gate. Okay, you remember that it has to be applied to this another AND gate. So this I am applying to this particular another AND gate. Okay, now the another input to this AND gate is this output. Okay, this is our third OR gate output. Okay, here you can see in this diagram, this is our third input. Okay, that has to be applied to this particular AND gate. So here you can see that this has to be applied to at this particular point. Okay, so I have made this connection now, and then this has to be again applied to this particular C. We have applied this B. Okay, fine. So now this has to be applied to this particular another AND gate. Fine. So I am just connecting to this another AND gate, and now the fourth output has to be connected to this. Okay, you remember that. So how to apply this one, fourth input? Here you can see this fourth input is nothing but this one. Okay, so this has to be connected to this, and now this has to be connected to this again, a similar fashion, and then finally we have to connect this OR gate, this OR gate to this particular AND gate. Okay. So here I have just made this connection, and this will be our final output that has to be connected to our LED. Okay. So you please try to make this all connections. Obviously, it is going to be a very complex circuit. Okay. Even if you implement the same thing on the breadboard, it is going to be a very complex circuit. Okay. But now you can see if we have performed or we have connected this all the means inputs properly, then obviously we are going to verify the truth table. Otherwise, if there is some mistake, obviously we are not going to get this result. So try to see this. This all are now 0 0, ABC is equals to 0 0. We can execute it, and we are supposed to get this output equals to 0. So here you can see that this LED is not glowing when we are executing it. Okay. So now you can make this combination 0 0 1. So just you stop it, or even if you don't stop it, because it is an interactive means digital constant, we can directly press a button C. So I'm just pressing the button C on the keyboard, so you can just check out this variation. Okay. I'm just pressing C. So now it has become 0 0 1. Okay. So this LED is not glowing. So here may be a certain error in this particular circuit. Okay. Obviously, some connections have not been made properly. Otherwise, this circuit has to be glowing. Okay. Because here you can see this. This is our functions that we have realized. So for the second combination 0 0 1, this has to go to 1. Okay. But it is not output is not glowing. It means that I have made a certain mistakes in this particular case. So let me see what is the error. Okay, and once we will able to remove this error, then only we can get the proper output. Okay, there must be some error because we are not able to verify this truth table. So let me just take a look onto the Boolean expression that we have obtained. There must be something wrong, otherwise the output should be verifiable. So let's see that whether this expression is rightly written or wrongly written. So here we can see that for this first combination 0 0 0, here you can see that if we write the max term, we are going to get this as A plus B plus C. So this is our term is corresponding to A plus B plus C, and this is we have already implemented. So this is a right term. Another max term that we can obtain is corresponding to this 0. So this is 0 1 0. It means that the corresponding max term should be your A plus B bar plus C. Okay. So here you can see that this is our wrong term. This is A plus B plus C bar. Okay. So this is not corresponding to this max term. Okay. So corresponding to this max term, we have this term at this point. Here you can see that this is our A plus B bar plus C. So this term is okay. And then again, you can see that for this combination 1 1 1, we will be getting this max term equals to A bar plus B bar plus C bar. So this term is also right. So here we can see that in this particular expression, we are actually having two wrong max terms that is written. Okay, so that has to be corrected, and accordingly we have to make the connections. So basically we are going to get the 5 max terms. Okay, you can see in which this first max term is okay. This third one is also okay. A plus B bar plus C, A plus B bar plus C, and then This fifth term is also okay. Now we have to actually make a correction for this two max terms, which is a plus b bar plus c bar and a plus b plus c bar. Okay, because these are not the right max terms. Okay, so corresponding to this 110. Okay, corresponding to 110, we are going to get the max term that will be equals to a bar plus b bar and c. Okay, that we are going to get a bar plus b bar plus c. That will be our max term corresponding to this. And similarly, corresponding to this 100, we are going to get the max term that will be equals to a bar plus b bar plus c bar. Okay, so that we are going to get. So sorry, it will be a bar plus b plus c. Okay, so these two term has to be corrected. Okay, that this two term has to be corrected because these are wrongly written over here. Okay, so I'm just making this connection. Okay, I'm just making this correction. Okay, and accordingly we have to make the connection. So here you can see that I also explained you this. Okay, first we have to take this f bar and then you have to calculate the complement of this. So once you will be doing this complement, you will be able to get the max term. So because this max term is wrongly written here, and we have made the connection accordingly, and therefore we are not able to verify the truth table. So I'm just making this reconnection, okay, because this is a plus b bar plus c bar is correct term. I have already implemented it, so this will be retained same. Okay, then again I have made this connections also, which is also correct term. Okay, a plus b bar plus c, this is also a right term, and then a plus b plus c. These three max terms are correctly written. Now we have to make correction for these two terms. Okay, a plus b bar plus c bar, and for a plus b plus c bar. Okay, these two corrections has to be made. So our actually term that we are going to get is one will be a bar plus b bar plus c. Okay, so in place of this, okay, you remember that in place of this I'm going to change it. Okay, and that will be equals to a bar plus b bar plus c, corresponding to this combination a bar plus b bar plus c. Okay, so that we have to implement. So yeah, I'm just going back to our circuit. So that was actually connected at this point. Here you can see that this is our first combination. This was our first output. So we have to make the correction for the second OR gate. Okay, for the second OR gate. Here we have to make the correction. Okay, and that output should be a bar plus b bar. I mean, this input to the OR gate should be a bar plus b bar plus c. Okay, so then that I'm going to make a correction. So here you can see this is our input. Okay, and that has to be our a bar. Okay, you remember that that has to be our a bar. So I'm just trying to make this connection. I'm just removing this connection first. So let me do this correction. I'm just deleting this connection first. Okay, I have already deleted it. Now I'm just making this connection to your a bar. Okay, that should be connected to a bar. Then the another input should be our b bar. Okay, just you try to see this one. So this is actually connected to your b bar. Fine. So now this is already connected to b bar. So this connection is right. And now this input is connected to another our OR gate, and then the another input to this OR gate should be your c. Okay, just try to see it is connected to c bar. So I'm just making a reconnection. I'm just deleting it. And I will be making this connection with the c. Okay, that has to be connected to c. Now we have corrected this one. Okay, I have just made this correction. Okay, that will be equals to a bar plus b bar plus c. And now I have to make another connection. Okay, that will be corresponding to this term a plus b plus c bar. This has to be this term should be your a bar plus b plus c. Okay, just to try to see this, that should be equals to a bar b plus c. That will be corresponding to this particular combination 100. Okay, so this should be a bar plus b plus c. Okay, that we have to make connection. So that is corresponding to your fourth OR gate. Okay, so just to go back to the fourth OR gate. Okay, in the circuit. So here I have just made like 1, 2, and 3 and 4. Okay, this one is the fifth one. So just try to make for the fourth gate. So in the fourth gate, we should be connected to a bar. So here you can see that it is connected to a. So I'm just deleting this connection again, and just you make a connection with the a bar. I'm just making this connection with the a bar. So now it is connected to a bar, and the another input should be b. So here you can just test it. I'm just checking it. So okay, it is connected with the b. So it is fine. So its output is connected here, and then again the another input should be your c. Okay. So this should be connected to C. So here it is connected with the C bar. I'm just making a reconnection, just delete this connection, and then you try to make this connection with the C. Okay. So hopefully if this is a proper connections, okay, then we should be able to verify this all combinations. Okay, so let's run this again. So if we execute it for the first combination all 0 0 0, this LED should not be glowing. So first combination is verified. Now we have to make it 0 0 1. So once you will press the C button, okay, so now it is 0 0 1 is now verified. It should be glowing. Here you can see that in the truth table, it should be 0 0 1 and this should be glowing. Okay, so now it is glowing here and we are able to verify our second combination. Similarly, I can make it 0 1 0. So first I'm just making this C equals to 0. Okay, and then I'm making this B equals to 1. Okay, I'm making this B equals to 1. So in this case, 0 1 0, this output should be a 0. Here you can see that for 0 1 0, this output should be 0. Now we have to test over this fourth combination, which is 0 1 1. So that time this output should be high. So I'm just making this C equals to high. Okay, here you can observe that C is equals to 1. So now here you can see that this LED is glowing and we are able to verify our truth table for the combination. Okay, now I can make it 1 0 0. Okay, I have to make this 1 0 0. So I'm just making this C equals to 0 and B equals to 0 and then A equals to 1. So here you can see that when it is 1 0 0, you can see that this output should be equals to 0. Now I can again test it for 1 0 1. So I'm just making it 1 0 1. I'm just making this C equals to 1. So I'm pressing it C. So here you can see that this LED is glowing and we are getting the right output. Okay. Then again I can make it 1 1 0. So here again I can make it C 0 and then I can make this B equals to 1. So it is 1 1 0. So corresponding to 1 1 0, this truth table is equals to 0. Again for all the combinations 1 1 1, there should be output equals to 0. I'm just making this C equals to 1. So here you can see that this combination 1 1 1 is equals to 0. So this way we have verified our all the combinations, and you can see that in both the cases, okay, the circuits are different. Okay, here you can see that we have a different circuit in which we have done the sum of a standard product implementation. Okay, a circuit will be was actually completely different. First we have performed the in this case AND operation followed by the OR operation. Okay, and here we have first performed the OR operation and then we have done the AND operation. Okay, and we can find that the all these combinations, okay, in both the cases we are able to verify. So hopefully you must have understood that how to implement the circuit in SOP and POS form. So please try with another examples. You can try any of the examples and you will be able to form this type of circuitry. Okay, you remember that a very easy way of implementing the same circuit is to take this minimal forms. Okay, here it is a minimal form which is A bar plus B bar and C. Even if you implement this simple circuit, okay, you will be able to verify this truth table. Okay, because it is a minimized form. Okay, we don't need to have so many of OR gates and then 5 input AND gate. We don't require. Okay, so in this case, in this particular experiment, we have verified its canonical implementation. So please try to do it. Okay, you will be able to verify that both the presentation canonical POS form or SOP form, okay, or a standard POS form or SOP forms are actually equivalent. So hopefully you must have understood this implementation part. Okay, so do this and try to implement the different type of functions or given statements, either considering the combinations of 1 or by considering the combinations of 0 and the output. Okay, so hopefully you must have understood this. If you have any query, let me know with your comments, and thank you for watching this video, and stay connected with the channel for more updates. Thank you.